Okay, good afternoon, everyone. We'll get started. It is as part of the seminar series of the Research Initiative Geophysical Flows Lab at IIT Madras. We are happy to host Aravind today for his seminar on locating subduction zones in the upper ocean using surface signatures. Aravind finished his BTech and MTech at IIT Madras in aerospace engineering in 2017, worked for a year as a project associate at IIT Madras before starting his PhD at the Northeastern University in 2018. And as part of his PhD, he has been involved in this Calypso program. And I think he's going to tell us about some of the research that he has been doing as part of this program and his PhD thesis. Arvind, the floor is yours.
Okay. Thank you for the introduction, sir. So good afternoon, everyone. It's great to see all of you here. I see some familiar faces here as well, so that's great. So yes, my name is Aravind, and today I'd like to talk to you about some of the work that I've been doing as a PhD student with Professor Michael Allshouse at Northeastern University. And of course, none of this work would have been possible without the help of some of our collaborators from UCSD, WHOI, and MIT who gave us very high quality numerical simulation data. And it was also great working with Helga Huntley and Denny Kerwin from Delaware, especially when I was working with ocean drifter data sets. I'll be talking about that towards the end of the talk, so we'll hold off till then. So basically today I would like to talk to you about how to locate subduction zones in the upper ocean using just ocean surface signatures. So I'm trying to use signatures, 2D signatures from the ocean surface to locate signatures of 3D processes in the ocean. So this work was done as part of a project that was a departmental research initiative that was funded by the ONR, which is called Calypso. And the basic aim of Calypso is to observationally investigate subduction in the ocean and try and understand things a little better. So the image you see here on the background essentially show 25-day trajectories of instruments called surface drifters that were released in the Mediterranean Sea as part of our last field experiment in the Mediterranean. And so what are surface drifters? So they are essentially instruments that have a buoyant top so that it floats on the surface of the ocean with GPS sensors inside. And then you also notice that they have these drogues underneath, which allows it to follow the motion of the fluid and minimize the effect of wind on the drifter. So why were they deployed? So there were a few reasons why they were deployed. One is that even though we deployed all these drifters in a very tight cluster, you see that over the course of a few days, it was able to give us a very good idea of what were the flow features in the region. So there's this large Western Alboran gyre that's over here. Most of them get caught in a jet of water that enters from the Atlantic on the west side of the Mediterranean Sea, and some of them get caught in a gyre here, but most of them essentially just go through this jet that meanders around. So why did we deploy a cluster of drifters for this experiment? Well, we wanted to know the flow features, and we also wanted to know if there was some surface convergence on the ocean surface. Because if there is convergence on the surface of the ocean, it would mean that there is downwelling, and downwelling is directly related to subduction. Now the question though is, what is subduction? Well, subduction can be simply defined as the downward transport of fluid from near the surface of the ocean to the interior. Now, that might be a simple way to put it. There is a slightly more rigorous way to define it, but we don't have to go there right now. We can talk about it at the end if needed. But essentially, what occurs during subduction is, especially at density fronts that we often encounter in the Mediterranean Sea, is that we see some dense water meet fresher, lighter water at a density front. And as a result, the denser water gets pulled underneath the lighter water. And as a result, it pulls some material that's usually found near the surface down with it as well. So the vertical displacements associated with such subduction, if you compute the average vertical velocities, it comes out to be an order of magnitude larger than typical vertical velocities that you would encounter in the ocean. Now, this particular picture was taken out of a study which was talking about where to go whale watching. So they give us examples of copepods, which are fairly large zooplankton that gets abducted down along with the denser water, which swim back up to the sunlit layers because they need sunlight, resulting in an increased concentration near the lighter side of the front, which in turn acts as feeding grounds for whales. Now, what we are interested in as part of Calypso is just this process of subduction. And the challenge for us is that this does not really occur in too many places in the upper ocean. Essentially, only a small fraction of the ocean undergoes subduction. And over the course of time, people have realized that subduction tends to happen a lot more near density fronts, where you get this dense water sliding beneath lighter water. So, yeah, the as I told you, we have been targeting the Mediterranean Sea, where we tend to encounter density fronts a lot more often because there's dense salty water in the Mediterranean that meets this fresher water from the Atlantic. And this picture essentially shows you what the power of satellites are. Essentially, what is shown in color is the sea surface height that we obtain from satellites, and that allows us to compute the currents in the region, the surface currents in the ocean. And if you look at the surface currents, you can clearly see that there's a jet of water coming in through the Strait of Gibraltar, and there are these eddying features present. And you might remember that some of these features were revealed by drifters as well, from a Lagrangian sense, though. And here everything is in an Eulerian sense. So satellites also help us in other ways. They also give us maps of sea surface temperature, which can help us get an idea of what the density distribution is on the surface. And they can also give us chlorophyll maps. And these chlorophyll maps are also helpful to us in the sense that these phytoplankton, which show up as chlorophyll signatures, can be used as tracers to figure out if there are subduction events occurring. So for our experiments, what we essentially do is try to understand where the fronts lie from these satellite maps and try to go zigzag across the front, keep surveying back and forth. And sometimes we get lucky and we get features like these, wherein we see these tongues of tracers, chlorophyll in this example, that go deep down from the surface, and we find chlorophyll maximus where we normally would not expect. So looking at the numbers here, or essentially the vertical displacement magnitudes here, we can conclude that these are essentially a result of subduction processes that occurred in the past. And that is good. But the aim of the Calypso initiative is to try and understand or see the process of subduction occurring actively, and not just look at subducted water parcels which may have gone down earlier. So the key challenge associated with observing subduction is that we need to have an idea of where subduction is going to happen or is actively happening. So that has always been a challenge to us. And as a result, we need to come up with ways to figure out where to go and look for subduction. And when I think about locating subduction in the ocean, the first thing that comes to my mind is the vertical velocity. Why can't we just look at the vertical velocity distribution on in the ocean and figure out where subduction happens? Well, first off, the vertical velocity magnitudes in the ocean are a couple of orders of magnitude smaller than the horizontal velocities, which makes it very difficult to measure vertical velocities. And secondly, even if we manage to measure these velocities, it is really hard in the ocean to obtain accurate high resolution 3D fields. So that might not be the best way to go. Uh, so As I mentioned, in the ocean, it's hard to get 3D fields, but what is often available to us are surface fields in the form of satellite fields that I had shown you earlier. Or if we are along the coast, we will be lucky and we can get some nice high quality velocity information using high frequency radar. So my objective during my investigations in models was to come up with efficient surface metrics that would allow me to locate regions of significant subduction in the ocean. So, of course, since I was looking at models, I had access to whatever information I wanted about the flow fields. So, the first metric that I considered was, of course, the vertical velocity. And since it's not really measurable in the ocean, I just use this as a barometer against which I can compare the other metrics that I consider. The second metric I considered was the horizontal divergence of the velocity field. Essentially, this only requires the u and v, the horizontal components of velocity, which can actually be measured in the ocean. And it is also beneficial to us because if I look at the negative of the horizontal divergence, it tells me convergence. And convergence, as I said earlier, on the surface of the ocean will correspond to downwelling. The third metric I use is the density gradient, because we know that subduction tends to happen near density fronts in the ocean, and if density gradients can signal where the density fronts are, we are probably more likely going to find subduction zones. Now, these three metrics have been relatively widely employed in by oceanographers to locate subduction as well as for other applications. But the problem is that we are using these instantaneous Eulerian metrics to try and locate subduction, which is intrinsically a Lagrangian phenomenon that occurs over a period of time. So as a result, I also proposed the use of two other Lagrangian metrics that are related to the deformation of infinitesimal fluid patches in the ocean. So essentially, if I consider an infinitesimally small circular fluid patch at the initial time t naught, and I let it evolve over time in the velocity field, I can define a flow map f that maps the initially circular fluid patch to an elliptic patch at the final time tf. So the first Lagrangian metric I consider is called the FTLE, which tells us how essentially tells us how much elongated the fluid patch gets by looking at one of the singular values of the flow map gradient. How exactly this is computed is not super important right now, but if anyone has questions, I will be happy to take that up later. So essentially, the metric FTLE tells you how much normal repulsion is there in one region. And for the other Lagrangian metric, I consider the other singular value as well. And considering the product of the two singular values lets me talk about how much area contraction or expansion is there associated with the initially circular fluid patch. Now, the way these metrics are defined, if I do a calculation from Ti to Tf, initial time to the final time and forward time, I get repulsion and expansion using FTLE and dilation rate. So if I do a backward in time calculation, these metrics are going to tell me where the attracting and contracting zones lie. So one thing I want to highlight again is that all of these calculations are done only using the 2D surface fields. And using these metrics, I'm trying to locate regions where there's 3D subduction occurring in the ocean. Okay, so what I did was essentially take all of these five metrics and try to figure out which one works best at locating regions of subduction by analyzing three different models, as I mentioned, from the UCSD, WHOI, and MIT group. And I ended up getting qualitatively similar results for all three models. So the first model was a very high resolution uh, model of a density front. It had a 2-meter resolution, so it was able to resolve turbulence, and it had a 4 kilometer by 3 kilometer domain in the x and y direction. The second model was a slightly larger scale model, which still looked at what happens across density fronts. And this was a larger model spanning around 150 by 150 kilometer domain. And now the resolution was 500 meters. And the final model we considered was a realistic data assimilative model of the Western Mediterranean by the MIT MCs group. And today, for the sake of brevity, I'll just be looking at results from that model. So yeah, the domain essentially spanned 430 kilometers by 267 kilometers, and it had the capability to assimilate various sources of data like from moorings, from floats, even drifter trajectory data. And when I was doing my calculations, I made sure that all the grids on which I calculated various quantities matched at least the resolution of the grid on which I had data available. So the first step for me was to see how much subduction was occurring in these models and where these regions of strongest subduction was. So what I did was initialized a uniform 2D grid of particles at a depth of 2 meters below the surface of the ocean, and I let them advect forward in time for 12 hours. And I computed the vertical displacement of each of these points of each of these particles, and that gave me the delta C or subduction associated with each particle. And I've plotted this information at the initial time t naught. So essentially, if I look at this field and if I look at this really dark patch of fluid, what I understand is that if I initialize particles, or if I consider water parcels at this location at the start time ti and let it evolve over 12 hours, the water parcels that started here will end up somewhere in the ocean that is at least 40 meters or 40 to 45 meters deep at the end of 12 hours. Now, now that I've mapped out the subduction in this domain, the next job I had to do was compute each of those surface metrics that I had discussed and see how well each of them did at locating these strongest subduction zones in the domain. So are there any questions so far? Are things okay? Is the pacing all right? I'll be happy to take questions at this point before moving further.
Are there any questions? If you would like, you can also put your questions in the chat box. Then we can periodically check.
Okay. All right. All right. So if there are no questions, yeah. So now we have the subduction field delta Z. Again, for the sake of brevity, I'm just going to show you one Eulerian metric, the divergence, and one Lagrangian metric, dilation rate. So these are the fields that I've computed on the surface of the ocean. And immediately we see that both fields have share some similarities with the subduction field that you see on the left. And there is a chance that the dilation rate field might be more correlated with the delta Z field, because you see that some of these features here match the subduction field here, whereas you don't see those signatures in the Eulerian divergence field. Now, to understand this a little better, since I've tried to choose a metric such that the strongest regions in these metric fields should ideally tell us where subduction occurs, I choose the top 1% regions in all of these metric fields as our target zones for subduction. And I try overlaying these target zones on the delta Z fields. And we notice that the dilation rate targets indeed capture most of the many of these subduction zones, and the divergence targets miss many of these strongest subduction zones. Now, to quantify this information, I calculate a few skill metrics, the first of which is a complementary cumulative distribution function of delta Z, given target zones of one particular metric. So here I have data for all 5 metrics and also for the no metric case. But what do I understand by looking at this curve? So if so on the x-axis I have 10 meters, 20, 30, and 40. So if I draw a straight line upwards and look at the blue line, exactly where the laser pointer is, what I understand is that if I consider the dilation rate target zones, I will be able, the probability of identifying subduction of at least 10 meters using the dilation rate target zones is around 75% or 0.75 or more. So based on this information, looking at these curves, you see that the Lagrangian metrics clearly do much better than the Eulerian metrics. Of course, the density gradient performs the worst, and divergence and vertical velocity perform somewhat comparably well. But yeah, the Lagrangian target zones are indeed more likely to identify regions of strong subduction. But this is not the only key metric we are interested in. I feel it is also important to understand what fraction of the strongest subducting zones are identified by the metrics that we considered. So that is the second skill metric that I investigate. And again, the dilation rate and FTLE, the Lagrangian metrics, tend to capture a majority, or if not most, of the strongest subduction zones in the domain, whereas the Eulerian metrics identify less than half of these features. So that allows me to conclude that these Lagrangian metrics, the 2D Lagrangian metrics computed on the surface of the ocean, are able to tell us how the 3D behavior is, at least in the upper ocean. Now, the question is, how is this model analysis helpful? Because models need not always capture the dynamics in the ocean accurately. Now, I've also shown you some images here. The image on the left, for instance, shows you the sea surface temperature from a satellite. And on the right hand side, I have the sea surface temperature for the same time instant given by the operational model of the Western Mediterranean. And the domain you see on the left is marked in black on the right hand side as well. So one thing that was quite impressive to me was how well the model was able to capture some of these features that is actually there in the ocean. For example, this feature you see here, where there's a sharp front, is captured pretty well by the model. And some of these eddying features are also captured very well by the model. But the problem is, at the end of the day, this is still a model. Things can go wrong. It definitely cannot accurately capture the real conditions in the ocean. So there'll always be some sources of error which we need to account for. And the other thing is, doing such an analysis also will not allow us to locate sites of subduction ahead of time. So what is the solution? Well, we decided to do a similar analysis on ensemble forecasts of the domain of interest. So what do I mean by an ensemble analysis? Well, we had this one central realization of the simulation, the operational model of the Western Mediterranean, which I had analyzed earlier. And since the group at MIT that did the model simulation had a method to generate an ensemble set of simulations using one single central realization by perturbing either the initial or boundary conditions or various parameterizations that were involved. And this allowed us to analyze the subduction fields and the surface metrics for 191 ensemble realizations that they had generated for the domain. So the image on the left essentially shows you how much variance it can be there in amongst these members of the ensemble set. So essentially, the black lines you see here in the picture show you the trajectories of particles that start at this point in the central realization, and the other colored lines are similar trajectories that I had computed for each of the other ensemble members. So this essentially tells us that there is a great deal of variability in this ensemble set. So what I did to ensure that the metrics we considered are robust to noise and model parameterization was essentially see how well the surface metrics that I computed using just the ensemble set performed with respect to the subduction zones in the true realization. Essentially, I computed the surface metrics without knowledge of the true realization, and I did an ensemble average. And then I compared the target zones I obtained from this ensemble average field to the subduction zones in the true field to see how well my results did in the presence of noise. Well, if I look at the two skill metrics shown, which we had looked at earlier, the results from earlier are shown using solid lines. We see that for the strongest subduction zones, the Lagrangian metrics do almost as well as the Lagrangian metrics computed from the ensemble analysis do almost as well as those computed from the true realization that we had seen earlier, both in terms of the likelihood of identifying subduction zones as well as in terms of what fraction of the strongest subduction zones are being identified. So this allows us to conclude that these Lagrangian target zones, especially the dilation rate, which is what I've presented here, that are computed without the knowledge of the true ocean state, perform just as well as the true target zones, provided we have decent enough ocean forecasts that are kind of accurate. They don't have to be exactly the same, but as long as things match fairly well, these Lagrangian target zones perform very well at identifying these regions of strong subduction. And now, finally, the question that I ask is what happens if the model is really bad? Like, in some instances, there may be sudden wind events that occur in the ocean which cannot be predicted by the model. And that may throw the model completely off. And what we see in the model may not match what we observe in the ocean at all. So, what are the alternatives? Well, one could argue that we could look at these surface currents that we obtain from satellite data and compute dilation rates with the help of this. But the problem is that the surface velocities that we derive from these from satellite altimetry tend to be non-divergent, and as a result, we don't really see any area contraction or expansion associated with fluid patches. And as a result, we'll get zero dilation rates everywhere. That's not good. The other thing is we can probably try using HF radar, the high frequency radars that can give us fairly accurate surface currents. But the problem is this can only be used in regions near the coast. And if you're out in the open sea, this doesn't really help us. Now, what's the other alternative? Well, now during field experiments, we are deploying surface drifters, and they by definition are quasi-Lagrangian. When I say quasi-Lagrangian, they track the surface of the ocean or specific depths of the ocean in a Lagrangian sense. And since we are computing Lagrangian metrics like the dilation rate anyway, I think it's worthwhile trying to figure out how they can be computed using some instruments that are already being widely used by oceanographers. Now, to discuss about how this can be done, I'll take a step back to the definition of the dilation rate, which we had seen earlier as the logarithm of the product of the two singular values of the flow map gradient. Now, if I rearrange this equation in such a way that I multiply the numerator and denominator by pi r square, you essentially see that this numerator ends up being the area of the ellipse, the infinitesimal ellipse, and denominator is just the initial area of the circular patch. So if I consider this definition of the dilation rate, note that now I'm doing a forward in time calculation. So positive dilation rate would correspond to expansion and negative would correspond to contraction. So this form of dilation rate has some benefits when we are using drifter data sets to compute this metric. Essentially, drifters themselves are not infinitesimal. They have a finite size associated with them. And so there's no way that we go out into the ocean and we manage to track infinitesimal fluid patches. The fluid patches we consider will always have a finite size, and these finite size fluid patches can no longer be assumed to deform into an ellipse. So having the area ratio based definition of dilation rate can be helpful when working with finite size fluid patches. The other sources of error come from the finiteness in the number of drifters available when we go out for a field experiment. So essentially, if we want to track the evolution of a fluid patch precisely, we'll need an infinite number of drifters populating the entire boundary of the fluid patch, which is never going to happen because even if we deploy a large number of drifters, all of those drifters combined is just going to give us one single dilation rate value. Now, we'll probably need to make dilation rate measurements at different regions in the domain. So we probably need to look at try to do an optimization of the number of drifters versus the number of dilation rate measurements we need. So that's another constraint. And finally, these drifters come with some GPS units attached to them, which essentially tell us what the drifter position is at every point in time. And these GPS units themselves have some uncertainty associated with them. So the drifter positions that we obtain from these GPS units essentially will have an uncertainty of around 6 meters on an average. Of course, this can vary depending on the type of GPS units we use. But yeah, these are the three main sources of error when we use drifters to estimate dilation rates. And I basically did an analysis to quantify the extent of error when I do these drifter-based estimation of dilation rates. Once again, I would like to pause for a bit in case any of you have questions. If not, we can go ahead.
There are a couple of questions in the chat box, Aravind. Can you see it?
Oh, yes. Okay, so I noticed that Vikrant had asked, why did you not consider temperature as a variable? So that is a very good question, Vikrant. We do consider temperature anyway because the density of seawater is essentially, so when we consider the density, it usually includes both the temperature and salinity. And both of these components are important. And we are looking at density fronts. So I think it's more useful to look at density fields and density gradients when we are out on the sea and not just temperature. But of course, from satellites, it's easier to obtain temperature maps, and that's what we use as for our preliminary analysis on where these density fronts lie and where we can go for our experiments. So I hope that answers the question. And the second question is from Prafulla, which says, did you use the horizontal divergence at only one instant in the analysis? Did you check the usability of horizontal divergence from multiple instants? So to answer your question, I did consider multiple instants. The results didn't really vary too much. And so if you think about it, if you look at smaller and smaller time intervals of analysis, the divergence at the initial time instant seems to do the best job anyway. I have also looked at averaging out, doing a temporal averaging of horizontal divergences to see if the results change in any manner. And what I observed was that the results just become worse when I do a temporal averaging. But there is one important thing to note here, which is the Lagrangian metric dilation rate. If you do some algebraic manipulation turns out to be actually the Lagrangian average of horizontal divergence along particle trajectories. Does that make sense? If not, we can actually talk about this after the talk as well, because it might not be super relevant to what I'm discussing right now. Does that sound good? All right. Are there any other questions?
There was also a raised hand. If someone
Oh,
raised your hand, you wanted to ask a question, please go ahead. You can proceed, Arvind.
all right. Okay. Can you see my pointer moving again?
Yes.
Okay. All right. Thank you. All right. So now I'm interested in this area-based definition of dilation rates. Yeah. So now when I start considering drifters to track the evolution of fluid patches, I'll have to end up discretizing the boundary of these fluid patches. For example, if I consider a drifter triad, I'm just going to consider regular polygons in this analysis for now. So if I start off with a drifter triad such that the vertices of the triangle lie on the circumference of an imaginary initial fluid patch, these can end up anywhere along the final boundary of the fluid patch. And as a result, there'll be some errors, and I can compute a polygonal dilation rate called a delta NR using these areas of the drifter polygons. So that is going to introduce one source of error into the drifter-based dilation rate estimates. And if I try to quantify the error that accumulates by comparing these two fields, first off, let's probably take a look at how these fields look. So on the top here, I have delta 100, which means that I've started off with fluid patches that have an initial radius of 100 meters. So for every single dilation rate measurement, I've considered a small fluid patch of a radius 100 meters, and I've seen how it evolves, and that lets me compute the dilation rate. That's what you see on the top. In the bottom, though, instead of using circular patches, I've started considering regular triangles, essentially equilateral triangles. And that is why I have delta 300 here, 3 for a triangle. We notice that there's a lot of noise in this dilation rate field when I'm using a drifter triad. If I increase the number of drifters considered per measurement from 3 to 4, and I start considering, oh, sorry, I'm really sorry about that. So yeah, to understand things better, if I consider a profile along an alternating region of converging and divergent regions here, if you look at the green line from the circular patch result, that you can clearly see that there is a strong region of convergence followed by a strong region of divergence, and then this dilation rates are somewhat around 0 on both ends. Now, when I start considering a drifter triad, for some reason, I completely missed this convergent extreme. Now, why does this happen? Now, the literature on submesoscale flows near density fronts regularly talk about a process called filamentation, which is a process wherein fluid patches get deformed such that the aspect ratios are really large at the final time instant. So when something like this happens, even when the area of the fluid patch may decrease, which corresponds to negative dilation rate, as a result of discretization, we might get larger drifter polygons compared to the initial drifter polygons. And this is the reason why here we completely miss the convergent extreme and we get some divergence, like very high divergence. Now, my question next was what happens if I increase the number of drifters per measurement from 3 to 4? And we see that some of the noise has gone away, but still the field is still noisy and we still miss the convergent extreme. What if I consider 8 drifters per measurement? Well, now the field seems really, really smooth and seems comparable to the initial field you see on the top left. But if you look at the profile over this alternating region of convergence and divergence, it still misses this convergent extreme. So this kind of suggests that most of the errors associated with drifter-based estimations are likely going to be concentrated near the strongest convergent regions, which can be bad for us. We'll see that soon. So now if I try to quantify this error because of discretization, we see that the error increases as a function of r and decreases as a function of n. Essentially, if I increase the number of drifters per measurement, the error decreases, but as we increase the size of the initial fluid patch, the error as a result of discretization alone increases. So the key takeaway from here, so the main reason for this is filamentation, as I discussed before. But the key takeaway from here is that boundary discretization, or essentially the number of drifters used per measurement, sets the upper bound on the initial deployment radius for our drifter cluster. The other thing that we can notice here is that there is significant improvement as we go from n equals 3 to n equals 4, and only marginal improvement beyond, which kind of tells us that n equals 4 may be a good balance between the number of drifters being used and the number of dilation rate measurements we need to make. Now, looking at the error magnitudes, the maximum error is still around just 3% for the entire domain when I do a spatial averaging over the entire domain. So that's still okay. And I would have been happy if I could just stop here, since the error magnitudes are so low, but I cannot, because we need to talk about the GPS units that are being used in drifters and the uncertainty associated with the drifter positions. So what we did to understand how accurate these GPS units were was essentially tie some of these drifters down to a dock and just took 10,000 samples of GPS readings for the drifters that were essentially stationary. And we obtained a Gaussian distribution with a standard deviation of 6 meters. So this is essentially the uncertainty associated with the drifter positioning. Why is this important? Well, now as a result of this GPS uncertainty, we no longer know where the final locations of these drifters are. And as a result, the drifter polygon that we see may end up being a distorted triangle instead of the yellow triangle we have been looking at so far, which allows us to control a new, to compute a new form of dilation rate, delta NR sigma. Now, the first thing I wanted to know was how much error was GPS uncertainty introducing on top of the discretization error. So first, I look at the effect of this versus this. And if I plot that, we see that the trend has reversed. For larger R, we see very little error. And for smaller R, we see large magnitudes of error, around 30% error. So why does this happen? Well, if the initial deployment radius r is very large compared to the GPS uncertainty, the GPS uncertainty doesn't really play much of a role when we look at the final distribution of drifters. Whereas if r is comparable or smaller than sigma, it might be the case that the triangle we see is probably just a result of noise even, especially if I look at the smallest radii considered. So this is the main reason why the trend is reversed in this case. And now the error magnitudes are very large. So drifter-based estimations of dilation rate are subject to all of these factors. And so if I look at the total error, uh, of course, GPS uncertainty sets the lower bound on R. And so if I look at the total error, the curve forms a nice envelope over the two curves that we have seen so far, which allows us to pick out an optimal deployment radius to obtain the most accurate estimates of dilation rates using drifters. So it turns out that if I look at the entire domain, if I choose 4 drifters, I can get away with less than 5% error if I deploy things at 250 meters. Now, am I interested in the entire domain for my application, which is subduction? No, I'm interested in convergent regions. So if I do the same analysis and do the spatial averaging over the top converging regions, we still obtain the same optimal release radius. But now, even for the optimal release radius, we see error magnitudes that are as large as 30%, which brings me to my question, which is, are these drifter based estimates of dilation rates useful at all? Because the error is just too big. So this is when I think I have to remind myself that I don't really need these dilation rate magnitudes. I just need to know where the regions of strongest convergence are. So this is often the case for other oceanographic applications as well. For example, for pollution mitigation, to see where all the pollution, all these plastics and other flotsam gather and converge on the surface of the ocean. Or if you're looking for bio hotspots on the surface of the ocean, you generally just need regions of convergence, and you usually don't need to know the degree of convergence accurately. So I did a quick test on how well these drifter based dilation rates locate the strongest regions of convergence as identified by the true dilation rates that I have been looking at throughout the talk. So in this picture, I have considered an initial deployment radius of 50, which was far from the optimum. And in green, I have plotted points in the domain where which are identified as strongly converging by both the true dilation rate as well as the drifter based estimate. The false positives are plotted in blue. Essentially, these are the points that are identified as strongly converging by the drifter based estimates alone, and false negatives are plotted in red. So for r equals 50, I think the results look good. We see a 57% overlap, as in 57% for green, which says that the strongest convergent zones, as identified by the drifter-based estimates, do well 50% of the time. And if I now look at the optimal deployment radius I had shown earlier, which is a radius of 250 meters, I see a very large value of 84%, which is uh, really good, I think, because even though these dilation rate measures correspond to 30% error or more, they are still able to successfully identify 84% of the strongest convergence zones. Now, you can also ask the question of how does this percent overlap vary as a function of deployment radius? That is another skill metric that I can look at. And even when I look at this, for the optimal deployment of radius, optimal deployment radius I had identified earlier, which is 250 meters, which I'd seen earlier. I get 73% overlap for drifter triads and 84% for drifter tetrads, and they seem to be the optimal based on a percent overlap kind of analysis as well. So to conclude, even when I don't have reliable model fields, we can still use drifter trajectories in the ocean to figure out where these regions of strong convergence is. And that can in turn be used to locate regions of strong subduction in the out of plane direction. So those are my conclusions. Dilation rate target zones are more efficient at locating regions of strong subduction, more likely, as well as identify most of them. Even if we don't know the true oceanic fields accurately, if we have a reasonable estimate of what the ocean conditions are from model forecasts, the ensemble analysis still does a very good job of identifying subduction zones. And the worst case, if models perform really, really bad, we can still use information that we can gather from the ocean to estimate good dilation rates. And that marks the end of my talk for today. And this is basically me from our last cruise we had gone in 2019. And I'll be happy to take questions if you have any.
Thanks, Arvind. Are there any questions for Arvind?
Hi, Nihar. I see you raised your hand. You can go ahead.
Hi, Aravind. Can you hear me?
Yes, I can hear you.
Yeah, it was a very nice talk and a very new topic, and I really like your work. I have some questions. I will ask one by one. You can answer them. So,
Okay.
when you talk to the drifter, like what is the depth to which it is dropped, like 15 meter or 10 meter, 5 meter, the measurements?
Okay. So thanks a lot for that question. So when I was doing these model-based analysis, I was just considering drifters on the surface of the ocean. And the example drifter that I had shown earlier, which is called the card drifter, has strokes that extend only over the first 1 meter of the ocean. So you do get drifters that track the surface of the ocean pretty well as well. But then you're right, there are some other drifters that can track what happens at 15-meter depths or even deeper. But we can just choose what level we want our drifters to be in.
Yeah. And another question is that in Mediterranean Sea, since it's a very new area as an for an oceanographer, for me at least, so
Okay.
is it a salinity control, density, or a temperature control there?
That's a very good question, actually. So, the most recent cruise I was on for this experiment was in February. And what we had noticed was that in the Mediterranean, more often than not, salinity was compensating for temperature. So, oftentimes you notice that warmer waters tended to be denser.
Yeah,
So,
correct.
that could be the case as well. So,
That is
sometimes it's
that is
important to look at both
temperature
temperature and
control.
salinity.
Okay, and on the western side, you have the Atlantic region, right? And you have
Yes,
that fresh water that is coming into that salty Mediterranean Sea. So, what is
yes.
the typical gradient of density that you observe? Like the gradient of density is higher in the western region of the Mediterranean Sea or in the eastern region of the Mediterranean Sea?
So densities will be higher.
Gradient,
uh
gradient.
Gradient, okay. That's a good question. I don't really know it off the top of my head, but I would expect that the density gradients would be larger towards the western edges, because by the time the Atlantic waters travel eastward significantly, I'm guessing there would be some sort of mixing happening. So the gradients won't be as strong, is what I would expect.
Yeah, okay. And the other question is that the last question
Mm-hmm,
uh, about the subduction that you have shown. I was
mm-hmm.
seeing one picture of Amala Mahadevan's vertical W. So it was
Yes.
showing that subduction zone can go up to 120 meter, and the delta Z that you have shown, it's about
Mm-hmm,
40 meter. So whenever
mm-hmm.
there is error, is it that the model is not able to capture the deeper depth, the deeper subduction? The
That
method
is
is that
very sharp of you, though.
huh?
So that is a very good question, and I would like to address that properly. So the subduction example that I had shown. Uh, are you referring to the chlorophyll image that I had shown, in which there
Yeah,
was a tongue that extended
yes,
to
yes,
100 meters?
1 and 20, yeah, about.
Yes. So that is something that had occurred over the period of a few days, and those
Okay.
water parcels didn't may not have really started near the surface either. In my analysis, I considered water parcels that started very close to the surface, and I did only a 12-hour analysis. I did observe, so I did check this, so I'm not just making it up. So if I do a longer term analysis, I do observe deeper subduction.
I see, I see, I see. And
Yes.
also, when you launch these particles, like
Hmm.
the particles across that circle that you have measured, like in the
Hmm.
form of triangle, and you were constantly increasing the number of particles, like three, four. I saw in one of your plot that delta
Hmm.
100, something like that, if I could remember. Is it that you were increasing the number of particles in that circle as you are doing the error estimates?
So if I look at this slide, would it be okay? Because I have delta 3, delta
See,
4.
see, what is this delta 100?
Okay, so when I say delta 100, I am writing dilation rate as delta n r. The superscript is n and subscript is r. So the
Okay.
100, so this is my fault for not being very clear. The 100 essentially refers to the initial radius of the circular patch that I'm considering.
Is
So
it 100 meters?
essentially, yes. So essentially, I'm considering 100-meter circles, and I'm deploying 3 drifters on the circumference of these 100-meter circles.
Okay. Okay. And 8 means that number of particles that you have taken in that circle, right?
Yes, so I'm not considering a triad anymore. I'm considering an octet. So there are 8 drifters on the circumference of the circle.
Okay. Okay. And just
That
last
is,
one question.
mhm.
I'll
Okay.
end here after asking this question. So basically, why I'm asking is that, so
Uh-huh.
you have the metric that you have used is log of area by area, right?
Yes.
So it is something equivalent of variance by variance, right? If you
Yes.
variance by variance. So suppose in this metric that you have taken, like in a circle, if you rather
Mhm.
than taking say 8 particles, say you take 100 particles or
Yep.
some large amount of particles, and now you compute the variance initially, and as the variance changes with respect to time, because the problem that you had in one of your slide, the way you explained the filamentation, that was
Mhm.
excellent. So will that improve your calculation if you increase the number of particles in the circle along the radius,
Mhm.
and rather
Yes.
than taking the area by area, you just calculate the variance by
Uh,
variance. So it is
did
also equivalent. Yeah.
uh, a quick question. Are you saying a radius or variance? I'm not able to hear you properly.
Okay. I am saying variance.
Variance. Okay.
So what I'm trying to say is that when you take the particle, so
Mhm.
basically the idea is that you have taken logarithm of area by area, right?
Yeah.
So it's a multiplication of two quantities.
Okay. Yes.
Now, if you in the circle, rather than taking that area,
Mhm.
because you have a formation of filamentation and you are not able to exactly calculate the area,
Yeah.
would be the variance. Say, for example, you have 100 particles randomly
Yeah.
oriented in
Mhm.
that circle, and you
Yeah.
follow in time
Mhm.
as the particle moves, they changes the shape. How the variance of the particles changes in time. So basically, variance by variance, logarithmic of variance of the final patch of tracer by the logarithm of variance of initial patch of tracer by 1 by time, rather than not using the area as the metric.
Okay. So I think I'm getting an idea of what you're getting at. I'm just not super clear on what you mean by variance of these particles, but I would really like to talk to you about it later if you have time. But there are some ways to compute some of these metrics using a least squares approach,
That is,
wherein you
that is
do take a,
yeah,
sorry?
that is the area I'm trying to go
Okay.
into.
Okay. Yeah. So there are some methods which can be employed that looks at variance, these least squares based
Yeah.
approach.
So
Those could
basically,
be used as well.
so your error might reduce comparatively. First of all, you have done a very nice analysis.
Okay.
For further improvement, probably if you can go into that direction, might be very much helpful.
It might be helpful. I agree. So I did look into this least squares based method as well, but I only looked at n equals 3 and 4. I did not consider higher n because I developed this direction and least squares did not really fit this direction I had. But what I had observed for triads and tetrads, n equals 3 and 4, is that the area based method and the least squares method gave me comparable results. But as you mentioned, if I look at larger n, there is a very good chance that the least squares method might do much better. Yeah.
Thank you, Arvind. Hope we will
Thanks a
talk.
lot for the questions as well.
Okay, bye.
Bye. I noticed that Prasoon has raised his hand as well.
Yeah. Hello, you able to hear me?
Hi, Prasool. I am increasing the volume on my end. Can you just try once again?
Yeah, am I audible now?
Yes, you are.
Yeah, Aravind, it was a good presentation. Uh,
Thanks.
yeah, I just wanted to know what is the resolution of your grades means. from one grid point to another grid point, what is the distance of in
So
your?
I have a 500-meter resolution in both X and Y.
Okay, so this data that you are using is shared to everyone, or is it like a closed group data?
So
Since I
I
was also working on ocean surface, I
okay.
just
Are you talking about the model simulations?
means this Mediterranean Sea
Okay.
that velocity that density
So the
data.
data at this resolution may not be available because it tends to be huge,
Okay,
but slightly lower resolution data is definitely available. And if you get in touch with this group, I am pretty sure you should be able to get your hands on the data.
okay. Can you just
If yeah,
I missed that. What group was that? Can
yes. So this is by Pierre F. Lermosio's group at MIT. I can just go to my. Uh, if not for this data, there is some publicly available data as well. If you look at the website of SOCIB, SOCIB is essentially it's essentially SOCIB. So you should probably take a look at their
SOCAB.
website.
Okay,
SOCIB. They have
okay,
publicly available data, but the resolution would be around a kilometer by kilometer, I think. I'm not
okay,
entirely sure, but you can just take a look and it's all
okay.
available there.
And this group, what you are saying is which one among this?
The fourth one from the left, the MIT group.
Okay, okay. Patrick.
Are there any other questions? Aditya has raised his hand. Aditya? Aditya, are you there?
Okay.
Go ahead, Aditya. If your mic is not working, you can, yes, you can type in your
Okay.
question. No problem.
Oh, that's a very good question as well. So for all of my analysis here, I have matched the integration time for dilation rate or FTLE calculations with the subduction rate calculation, which was 12 hours. And I have also done other calculations in which I vary this if you're interested. So sorry. Yeah, essentially, even if I vary the time in integration times, I still see that the Lagrangian metrics perform better than the Eulerian metrics in this panel C. If I tell you a quick summary of the result. Sorry.
Are there any other questions from others in the audience? If not, I would like to thank Aravind for this interesting talk. Yeah, satellite data is available at daily resolution. Can FTLE be used for computing? What was the message?
Oh. So, Aditya, FTLE cannot be used for computing subduction. So, from my analysis, I understood that FTLE computed in a backward in time sense can tell you where these attracting zones are, and that can tell you where subduction can occur, but it's not going to tell you how much subduction is going to occur. So to answer Prasoon, the satellite data is not divergence free. If you obtain the sea surface height from satellites, essentially you use the geostrophic balance using geostrophic balance and the hydrostatic approximation, you are able to obtain the u and v components of the velocity, and the velocity you obtain in this manner tends to be divergence free. All right.
I am not fully sure of that, Aravind. You may want to check.
Okay, I will double check, and we can talk about that as well, sir.
Yeah, sure.
Okay.
Okay. Thanks a lot, Aravind.
Thank you,
That
sir.
was a
Thanks
very
for
interesting
the...
talk.
Yes, thank you.
Plenty of nice questions as well.
Yes, thanks a lot for the questions. They were really good.
Yeah. So if anyone is interested in discussing further with Aravind, is available for the rest of the day on campus here at IIT Madras, or I'm sure you could reach him by email as well.
Yes.
Thanks everyone for joining in.
Thanks a lot,
Aravind.
everyone.
Yeah.